Buenas tardes y
Good evening and welcome to this new conference on mathematics at the Residence. This program is organized by the Institute for Mathematical Science in cooperation with the Deputy Presidency of Science in CSIC and jointly with the Residencia de Estudiantes. We've had very high-level scientists like Edward Kleffer, Tom Crawford, Marc Camacho, or Eduardo Sáenz de Cabezón, among others. In addition to adding and dooms to this list, we're celebrating the Day for Women in Mathematics, established to advocate the work of women in mathematics. The chosen date, 12th of May, commemorates the search of a mathematician, Mariam Izhaghani, and this happened only 49 years ago, which is surprising. Mariam Izhaghani was born in Tehran, in Iran, on the 12th of May, in 1967. Thanks to his contributions on dynamic system and the symmetry of curved surfaces, he received the Phillips Medal, one of the greatest awards in mathematics, awarded every 4 years to 4 researchers in mathematics who are under 40. She was the first woman to receive this award in 2014. In 2022, Marina Wiatrowska won the award. So in 2 months, we will know if we have a third one. We should not just complain about the scarce presence of women in the area of mathematics or the scarcity of women that have been awarded the Phillips Medal. We should also be sorry at the loss of Mariam Izhaghani at the age of 40 due to tumor. Let's commemorate her work and the work of many other women mathematicians. Let's do it through a top-level speaker. Anne Doomsch is a professor at the Mathematics and Data Science Department in the Vrije Universiteit of Brussels. Her work focuses on algebra and harmonic analysis combined with artificial intelligence, a much more modern discipline. She specializes in digital mathematics, which is about the theoretic fundamentals allowing for the recognition of patterns with a computer. This can be applied to medical image analysis of the cultural patrimony, forensic computing, or post-quantum cryptography. She holds lots of positions, among which she is president of the Education Committee of the European Mathematics Society. She's promoted a set of online seminars on mathematics education that I recommend you to watch on YouTube. Lastly, in addition to all her work, she's an amazing disseminator. She's written several books. She regularly participates in the written press, and she delivers amazing speeches like this one. An image says more than 1,000 words, but what language does it speak?
we are looking forward to your talk, so please, the stage is yours.
Gracias, María. Buenas tardes. My talk will be in English, and I will tell you all about images. So let's start with one.
I'm going to show you some magic. It's the real thing. I mean, it's all the real thing.
It's not. This is a deep fake. So this is not the real Tom Cruise. It's been created by a voice imitator, and then his face is transformed into that of Tom Cruise. These fakes, we've been seeing them around for a long time. A national pride, I think, Penelope Cruz. Well, this was the original picture. So this is the famous example of Photoshop. We've all been seeing how pictures are being altered. This is, of course, not on purpose. But we've also seen it's not only due to the age of AI that we've seen deep fakes, but this one, in 2008, it was worldwide front page news. This is a picture of missile launch, a test launch, by Iran. And yeah, it's to show their forces, right? But if you take a closer look, can you see something weird going on? If you look at the fumes, they're exactly the same. So chances that this will happen is non-existent. So with a computer, we can actually detect that this middle one is a mixture of these other rockets. It was immediately noticed on web fora, and SEPA News changed with the article the picture into this one, which looks less scary, so one of the rockets didn't launch. Now, you might think it's quite easy to detect this with a computer because it's just copy-paste. But it was actually detected by people with a good eye. Because learning a computer, even if it's copy-paste, is a very difficult computational problem if you would do it pixel by pixel. You cannot compare everything with everything. So you have to do this more smartly. And this is where mathematics comes into the picture. So I don't do crime scene investigation, but we do digital image investigation. And to explain you how you can do this with a computer in a smart way, I have to explain to you what an image to a computer actually is. So that's why I like to start with one of our Belgian prides, this painting of Magritte. Ceci n'est pas une pipe. It means that it's a painting of a pipe. It's not a real pipe, it's a representation. Well, every digital image is also a representation of reality, and it's one in pixels. But what are pixels? It actually tells you the light that is emitted from objects and that you take with photographs and that you take with cameras. And this light actually comes into 3 numbers, a number for red, green, and blue. And these lights values or intensities are being represented with numbers just ranging between 0 and 255. And with this, the beamer, your screen, of your television or your smartphone knows how to light up and actually represent this reality with these numbers. Now, to show you that this really works, I loaded this painting into Excel. If it's just numbers, I can read that out. It's not directly, but there are simple apps that allow you to put these numbers into Excel. Now, you see the structure of the pipe appearing. And why is that? Well, if I zoom in, I can see that inside of the pipe I have small numbers. I have zeros, 7, 8, 20, and outside I have numbers in 200. Well, 3 times 255 means white, and so numbers in the 200s is the yellowish, and 3 times 0 is black. So there I have the blacks and the browns. So that's what you see. Now, the lights on the screen actually only light up with this red, blue, and green color. This sounds very weird, so we don't actually have colored lights. It's just those lights lighting up with different intensities. So to show you that this works, I can actually imitate this in Excel. So I color these cells with red, green, and blue. So they are vertically grouped. So when it's small numbers, I make them dark. And when it's high numbers, they go to higher intensity. Now, if I zoom out, the people in the back will see colors appearing, while I only colored those cells with the 3 colors. So images in a computer are just matrices or tables of numbers. So a computer does not have to see at an image, it does not have to understand what's there the way we do. It can compute. Now, mathematicians were not the best computers. I don't like computing by head. But we are very good in inventing the transforms that you need and that you can put into a computer to tell him what is on a picture. Now, one of the most famous transforms that can actually help to detect pictures and to also look at these copy-paste is to investigate, in transforms that investigate or look for special groups of pixels. And one of these famous transforms was invented by this lady. We're talking about women in mathematics. This is Ingrid Tobuchi. You might have heard about her. She's an alumna of my University of Mathematics. And she invented the so-called Debussy wavelet transform. If I say wave, you hear the word wave. And they actually made a big source of inspiration. But if we think of waves, we actually first think of periodic signals. If we are looking around in nature, waves, tides, day, night, months, years, everything in our life is periodic. This was already discovered that this is a building block of nature by Fourier. And not only like in the big world around us, but also on a small level. If we heat objects, then the molecules start moving, and they are also moving with periodic moves. And Fourier created his Fourier transform, which actually allows to represent any signal that we can see around us by combining waves, so cosines and sines. And this combination you make, some of them are moving very slowly, others are moving very fast. And if you make combinations of these, you can actually represent everything. But you might need a lot of those wavy patterns. And you can also do this two-dimensional, because then you take these patterns moving horizontal and vertical. So one of these two-dimensional waves is actually one represented here. So we have peaks and we have lows, and this continues infinitely horizontally and vertically. This is a three-dimensional object, but I can actually think of it as a two-dimensional representation. And I can make this, I can make a picture of that. I can show this in a computer by just taking some discrete values from it. And then I color those pixels with the values that we have. So red when it's high, blue when it's negative, and white when it's zero. And maybe not a surprise, you can use those discrete pictures of these periodic functions to actually represent images. You can use those as building blocks. Now, I said, well, sometimes in practice you need a lot of them. And how would you on Earth be able to determine which blocks you need? Well, Fourier actually created his mathematical transform in a way that this the number of blocks and how you have to combine them, you can actually compute that. And you can compute that in a computer. Now, the thing is that, well, if you have to use all of those, the long ones, the ones that move very fast, that's not so practical. So what you do in practice is actually cut your image into pieces of pixels, groups of pixels, 8 by 8. So you take your picture and you cut it all in groups of 8 by 8 pixels. And those 8 by 8 pixels, these are the ones that we're going to represent by a combination of these 64 periodic patterns that we actually get from Fourier. So if we have like a non-moving or one color zone in an image, we can just use that one, and we multiply with the color value. Actually, we don't do this in red, green, and blue. You can go to grayscale and remember what colors you need to add. So you can think of images as grayscale, and then you have to adapt this color. If there's a lot of things going on, then you might need this one which is very detailed and combine this. And actually, if you zoom into pictures, it doesn't not work too much on a smartphone, but on a computer you can zoom in very well. If you look to these 8 by 8 blocks, it's actually, you can see that it is not so surprising that you can use these combinations to actually represent. But why would you do that? Why would I change the groups of pixels into this? Well, it allows you to actually look at the building blocks of an image, because then it can transform or lose a little bit of detail, but you can compare images to each other in terms of those building blocks. You can say, this image takes a lot of these very high periodic, or it has most of these ones. So it gives you a way of comparing images without actually looking at what is depicted. So it is an abstraction. It is a way that we as mathematicians, if we investigate functions, that we also like to look at bases or building blocks. And it also allows you to do compression. Compression is changing the space that an image takes on your smartphone or your computer by not remembering all the light values that your camera captures, but just how you, per 8x8 groups, need these building blocks, and then you don't have to remember the whole building blocks because you can just number them. You can say this group of 8x8 pixels, it is block number 4 plus this block, for example. This is taking way less space than remembering all of the 8x8 pixels. So it's a way of representing your image with building blocks that you number. So if I do this with Ingrid's picture, you can see I cut it in 8x8 blocks, and then this is transformed into these combinations of patterns that I need. Now, this is the basis of the well-known JPEG transform. We use this every day, pictures being saved in JPEG. It's also the basis of video. If we are looking at digital television, it's actually based on this JPEG. The thing is that a camera, of course, takes pictures at repeated times, but you're not going to remember all of these pictures. You actually remember some of the timestamps, and then you try to kind of predict what is in between. And that also gives you video compression. So the images that you remember are being compressed with those building blocks. And in between, you say, okay, those building blocks move like these or that. The thing is that, and you might have seen this, this happens a lot if you are watching football. If you're watching football and people are running and they suddenly move, and then you see things like this. This was me in an interview. I tried to speak slowly now for the translators, but often I go, I was speaking so fast that actually the video on television, I was not able to capture the way I moved my mouth. So these are blocking artifacts, we call them. And it's because, you can see these blocks, it's because we cut everything into these little pieces. Also, back in the 90s already, if we were using JPEG for compression, you needed a lot of compression to send images over modems. We didn't have the internet that we have now. And then actually on pictures themselves, you could see those blocks. And that was the time that Ingrid was actually thinking back of waves. How can we investigate images or put them into their building or divide them into their building blocks in a smarter way? In a way that you don't need to cut them in those 8x8 blocks. Because if you cut them in those 8x8 blocks, you're actually not really looking at what is on the picture. It allows you to store it smaller and to compare building block-wise, but you don't get a sense of what's there. So she was thinking, well, if I look at the sea, I have this periodic behavior, but locally, it changes. Here I have this part of the wave, so locally I have a lot of detail. There's a lot of things moving, and it's not periodic at all. So that allowed her to make a transform that actually literally uses building blocks of this type. And that's why they are called wavelets. She did not invent this type of transform completely. It already existed to investigate seismographic signals, which are also periodic, but that can move very fast over time. What Ingrid did was actually transforming these types of signals of blocks into really something that allows you to use it as building blocks, as a basis to reconstruct every image. And that's what made her very famous. So this is, again, if we would do it in one dimension, and similar as what we saw before with the Vrije basis, you can get building blocks like this. So they're much more spiky, and you also do it horizontally and vertically. We can, again, project them and take an image of it, and by making it discrete, and then these values change more. And then these are the accompanying building blocks. And you can actually see that those are not periodic, they are localized, but they're local periodic. And the way that you use them is, because then how could you now look at what is on a picture? Well, what she invented was we can study the structure of a picture by actually always downscaling it. And so you halve the resolution. How would you downscale a picture? Well, you just take weighted averages. If you take averages of pixels, then you can halve them horizontally, you can halve them vertically. And in this way, if you are constantly like lowering the resolution, what you will keep in the end are like really the big picture. What is the kind of big shape that is on there? And in the meantime, you lost all the detail. Well, all the detail you can capture with these blocks. So the way you investigate an image with a wavelet transform is that if the image was first the size of this whole thing, I downscale it by half, and I downscale it again, and I downscale it again, and there, in this upper left corner, you can actually see a 1, 2, 3 times downscaled image. And in the other parts, you can see the detail that I lost. And for this detail that I lost in downscaling, I can use those building blocks that we had here. So they allow you, because it's only detail, to then say, well, this detail is this block plus this block, for example. So you can do this in the same way as with Fourier, but now you use these blocks for the detail. And if I do this on Ingrid's picture, if I do this one time, what you see here is the way I can build up Ingrid again. So first, you saw it very low resolution, and then you can see that the detail is being added. Now, the way she first invented it for compression, I said it was in the 90s, to be able to send images over modem lines in a more efficient way without those blocking artifacts. The way, if you are looking at like the core structure, the averaged image and the details, it allows you to remove, for example, the details that are here, because we don't see this by the naked eye. But this is a lot of information that you would actually otherwise have to store. And all the other details, you can actually then choose one of the building blocks, and you can throw away quite some detail. So you can have a lot of compression using this way of looking at an image. So I will do it once more. So you can see her building up. This is like you add all the detail. This also allows you to actually send images over internet, and then if you just wait a little bit longer, it will become sharper. This is what it was being used in the beginning for. Now, why don't we see this wavelet transform? It's then actually the basis of JPEG 2000. Why are we still using JPEG? Well, it's a matter of patents. That's a little bit of a sad story. You see JPEG 2000 as the format in digital cinema, for example. So they are allowed to use the format. And you also see it in medical scanners, because it's a very good transform that allows you to store images at a much lower space than the actual image. Ingrid got famous because the first ones who realized how powerful her method was the FBI in the States. And each time you enter in the States, you have to take a fingerprint. All those images are actually also compressed with this wavelet transform. Now, Ingrid, she knew or knows that this mathematical transform of looking at structure in this way, the global picture and all the details, would allow you to do much more than compression. So she was always actively looking for what other applications would you actually be able to use these transforms for. And, well, Ingrid was the first female professor in mathematics at Princeton University. And there she started working on digital scans of paintings. And it's because one of her friends is curator in the Van Gogh Museum of Amsterdam. And there they actually have a problem that the Van Gogh Museum, of course, is all about Van Gogh. For some paintings, they don't really know if they're true Van Goghs or not. And then for some Van Gogh paintings, they don't know when he actually painted them, in which period. So there's a lot of ongoing research. And Ingrid thought like, well, my kinds of representation of looking at global scale and detail might help to actually capture the painting style of Van Gogh. And you can see it's this, the Starry Night is a very famous one. There's a lot of these prominent brushstrokes. Now, one of the, what Ingrid created, this mathematical transform, to decompose an image, it's not just one transform, it's a family of transforms. And you can look at specific ones that are looking at curved lines. But it's always the same principle. You look at curved lines which are at big scale, or the global structure, the global things, and then you can look at the details, and then you actually get information on these small ones. Well, as the States are quite far from Amsterdam, we got in contact and she asked me whether I was interested of doing this in Europe, and especially with the Van Gogh Museum. And we worked on a challenge that appeared on the Netherlands national broadcast television station. Because they were kind of, now we're talking about 2005, 2010. AI, nobody was talking about AI, but we were actually doing AI or machine learning. We were teaching a computer, so we got a challenge, which of those paintings is a real one? And another one is a copy made by a restorator from the museum in Van Gogh style. So you see, the picture, the person is completely the same, but like the paint itself, the way it's painted, it's a bit different. And the restorer did that because she knew we were going to look at the big details, but also the small details. Now, I hope you did not do this when you were little. I hope my daughter will not do this. Like, if you want to imitate the hand or the signature of a person, and you would want to do this very, very, very good, then you'll see hesitations. That's how people can discover whether a signature is being faked. So she thought, well, if I try to really, really get an exact copy of the real one, they'll notice this in this fine detail, because they can look at my brushstrokes. So that's why it looks a little bit different. Yeah? So this was on purpose. Then what we did was, one of the first big applications actually of machine learning was looking at a large number of high-resolution scans of real Van Goghs, decompose them with these wavelet transforms suited for directions and curved lines, and then actually translated Van Gogh's painting style into a sequence of numbers that represents him. And this sequence of numbers, you can think of that like, well, he mostly paints the large strokes, for example, in this direction. And the smaller strokes are like going in the other side. And can be like the way that, if you look at the birds, the way that you paint also depends on your wrist and the way you would hold your pencil. So you can look at which combinations of lengths and directions of strokes are actually appearing mostly in the Van Gogh paintings. You need a lot of them, because if you would just look at one painting, then you are of course also looking at what is depicted on the painting. So you want it independent of what is depicted, but really look at what is mostly the length of the brush strokes and the directions that are being used by Van Gogh. And this indeed allowed us to detect that this one is the real one and that one was the copy. Because the combinations really showed the way that the restorer was holding the pencil. We have to be honest, at the first it was very obvious, but it was, and you can see this picture is a bit more blurry than that one, so we saw much more detail there, so it already looked different. So yeah, we first discovered the high resolution scan, let's say, but then we did the comparison in a more honest way. And I'm actually happy to say that this research is continuing here in Spain, but in collaboration with the Courtauld Museum. We're actually, if we're talking about women in mathematics, we also have to talk about women in art. We have Sofonisba and Guisola, who work together with Alonso Sanchez Coelho at the Spanish court, and they collaborated, but we don't really know on the paintings who did what. So one of the challenges that we're looking at is from paintings that we know that are Sofonisbas and paintings that we know that are Alonso's, can we learn their style and then try to look at the combined paintings who did what. Now this is much more challenging than the Van Gogh paintings because these are, the brush strokes are not so prominent, so you have to look very closely and also a bit more globally because it can be that the faces, the way that they are composed are maybe a bit different from one to the other. So very interesting research. So it will come down to what is basically the style or the distribution, mathematically, that a painter is using. And, well, we as humans are very good at looking at distributions. And these are, if we're talking again about representations, 3 very different representations of cats. But kids, from a very young age, will tell you that these are cats. Well, it's picture-wise, it's something completely different. So a distribution of a cat, what is the pattern in a cat? What is making it look like a cat? Illustrators are very good at that because they make very simple drawings and we all understand that these are cats. Now, if you want to teach a computer that these are all cats, these wavelet transforms will not be enough. If we look at the building blocks, the details will be different, so we need something more. And that's, of course, where machine learning and neural networks are entering. We can learn a computer that these are all cats by showing the computer many, many, many examples of cats. Think of that, many tables of numbers with cats. And then a neural network actually makes just the way that the wavelet transform makes averages. It makes averages and then rounds those averages. And then so it makes averages, it rounds them, then it goes to a different dot that again makes averages of those averages and rounds. So the scale idea is very similar to the wavelet transform. Now, how does it then work? So I give these examples. It will first take random averages. And what you hope is that if you go through this whole network, that in the end you'll get a number very close to 1 is where cat is, and numbers very close to 0 where the other labels are. Of course, if you do this the first time at random, this is not going to work, right? I also give them dogs, and then I hope that the number there, it becomes 0, 1, 0, 0. Now, this is not going to work from scratch. Now, the good thing is again, mathematics comes in. If you do these random, then you look at these labels, and if they're wrong, you can actually correct. You go backwards to the network by looking at derivatives, what Newton and Leibniz invented. You can see how much is my number off from what I want, and then I turn the knobs. Of course, if I turn the knobs and make it correct for cat, it most likely goes wrong for dog. So you have to do this in many times. What is surprising is that it works. It will learn in those circles numbers with which you have to take averages. And it will detect building blocks, but not building blocks that we saw like with Fourier or with the wavelets that are fixed for every image. You'll learn building blocks that are suitable for categories of images. And you'll learn building blocks for cats, for dogs, and everything at the same time. And this is what was being used, actually, this type of network in the first video that I showed. What happened there is that a network was being trained on lots of images or films, movies of Tom Cruise. That's why you will see these deep fakes often appearing for actors or politicians, people of which many image or video data exists. And here you see the imitator. So this is the voice imitator. He looks a little bit like Tom Cruise. Now what we know, those networks, often it's said, oh, they're black box, but for images we already we know quite well what it is doing. So in the beginning, it will look again at these very small details, because we'll take averages and it will actually show you small details. And the further you go in the network, it's about how these edges combine. And then at the end of these networks, it's like objects. So faces, you could say, will be somewhere near the end. And then you can ask this network, well, actually, where you recognize the face here, swap with faces of Tom Cruise. Of course, it's not that easy. It's a very, very complicated engineering job, but that's basically what happens. You can swap those outcomes, those numbers. And then we can also do this with paint. I can make a Magritte pipe into Van Gogh style. But what would I have to do for that? If you understand that it first looks at small details and then shapes and then complete objects, now I will not ask to swap at the same place in the network, but to do a swap at different places. So I can say, to make this pipe, keep my object, so keep my outcomes at the end, but swap with the outcomes that you have here, so the beginning, so the details. And then I can make this pipe into Van Gogh style. If I do it the other way around, then I ask to keep the objects there, which are not so recognizable. But then what are the details there? It's not much going on, so that's a much less interesting painting. I can do this with this is the thinker on our VUB campus. Make some publicity for Bruselas. Van Gogh style. Kandinsky, one of my favorite painters, very nice style. Of course, I have to use the Guernica, right? Picasso. Nice. Another Belgian pride, the Ghent altarpiece from Van Eyck. I think you can imagine how it would look like. So you can think a bit of Sofonisba and Alonso. It's also this kind of a very detailed style. So you can imagine how it would look. But this is the result. Now, if you understand what I just explained, I asked the network to swap details. It does not see the difference in details between the green patches and the small faces. So these networks are so good at recognizing objects, but they don't understand what they're doing. And so, to them, they can do silly things. And for networks, it's still very difficult to see the difference between muffins and chihuahuas. Very easy for us. Snow owls and Granny Schmidt apples. Easy for us, difficult for networks. And this difficulty, it's about these patterns. If you look at it, they have something in common, but it still makes us a better pattern recognition. And this pattern recognition, it's all about giving enough data, of course. And if you don't do that, you can have this painful example. What we see here is an image from Google Photos. Allows you to upload many photos in your library. And Google is always very good in AI. They have won the Nobel Prize with the AlphaFold about using AI to predict protein folding. But sometimes things go wrong. So they were one of the first ones to use this object recognition for your library. Because if you upload all these images, you get so many images. So they were ones using the pattern recognition of neural networks to classify in your library pictures by type. So you could have the labels that were given by Google itself. So it recognized skyscrapers, airplanes, and what happened here? So what showed was that Google did not train enough on people with colored skin. And so then it looked at the color, what was closest to that. And then you get these things. So it's very, very important if you use machine learning on data, on examples, to use a representative set for your problem. Because it will always give you an output. It will always look at what is closest. It does not think. Now, how do you get all these examples? Well, there are people that are actually working as slaves, underpaid, labeling images for free, almost. But you are also a slave. Every time we answer a CAPTCHA like this, we are actually helping Google to label images which are a bit too difficult for them. What we see here is bridges. Bridges are mostly of this type, something horizontal, and then what is a difficult one? It's this. It's easy for us. We recognize this, but this is not a very nice, recognizable shape. They want this for their self-driving car, and they know some of them, like these are clear examples that the network will recognize. So you have to answer, they check whether you answered those that are known, and then it will add those if enough people label those as images. That's a test to prevent computers from automatically accessing accounts. So it's using the fact that neural networks are not good at selecting these. It's called CAPTCHAs. It's computer automated tests to tell humans and computers apart. That's because we as humans are better pattern recognitions. Now, we did recognition, but it's not all about recognition now. When I showed you this deep fake, it's of course also about generation. So if you want to do more than recognition, you'll have to learn the distributions so that you can actually ask, create me something that looks like that yourself. And one of the main mathematical ideas is in denoising diffusion. Diffusion is again something from physics, the way that heat dissipates. And the way that this works allows you to train networks to really capture much more broadly but very specific patterns, and then they can generate faces that are very, very realistic. I'll talk more about that tomorrow in the machine learning seminar. Now, so machine learning is very powerful. But then, like I said, it's not always very clear, or they don't understand what they're looking at. So you have to use them for the tasks that are controlled and in which they are very good. But when are they not so good? So not in understanding, but also not in things that are, yeah, maybe recognizable from this global shape. Even faces, you need these details, but it's still some global and then filling in with details. But sometimes you have problems where examples are looking globally kind of like a pattern, but if you look locally, they're very irregular. And the more examples that you give, it will be able to kind of recognize those patterns, but not up to very high detail. And where you would need that is when I go back to art. It's back to this Ghent altarpiece, where we saw this one before. When we were using machine learning to recognize style, we also got a question from art historians about the back panel. This Annunciation to Maria. There's a book. It's a couple of centimeters, it's not that big. Art historians, so we had high-resolution scans of this painting, but art historians were wondering for years, what is depicted here? Because the Van Eyck brothers, they are so realistic in texture, but sometimes if you look at, for example, pearls, if you look closely, it's just like blobs of paint. So they thought that also here, it's just blobs of paint giving you the idea of text. But if we look closer, then you see, well, maybe they're words. The problem for the art historians was that the cracks in the varnish are actually kind of the same, well, they're smaller, but it looks similar. So if you do pattern recognition, this network will actually detect and the text and the cracks. So you have to work more detailed. So you want pattern recognition, and that's again where mathematics comes in. So examples alone, showing examples like this is a crack or not, then you would have to do by hand, almost like this is one, this is not. And there you don't know. So if we reason about this mathematically, what does it mean for a crack? It's more small, it's more irregular, those are more aligned. You can get mathematical rules that come into play. And then you can create a computer program that detects them automatically up to pixel level. And then you can do generation. You can use AI to actually fill in the cracks and make lines continue. So this is the book as a whole. This is then the detected pattern, and this filled in. It's meant to be filled in here. There it looks more dirty, but you don't have to pay attention. You have to look here. And the art historians were able to read the words. And it brought them to a copy of Thomas de Aquino from 1430. And if you know that the painting, the Ghent altarpiece is dated in 1432, it's very likely that they used this. And so this is millimeter work. They painted really text from this. Now, from this crack detection, from damage detection, my research has a lot of serendipity. I go from here to there because people ask me and I think, oh, why not? Why don't we try this? I ended up working with the Library of Belgium in Brussels because they have many scans of newspapers, and you see that there are holes. If you want to use this is now, of course, better with AI, but we already are using, since the 90s, OCR, optical character recognition. Then these programs, they actually fail a lot when you have these damages because they don't understand that there is a damage. So they give you a lot of gibberish things. So you can do keyword search, but it's very difficult to extract the whole text. And if you, for example, want to run an LLM, like ChatGPT or others to kind of read what's there, it's complicated. So we created algorithms that can detect those damages, but then also can handle this because it looks like a very clean one. This one is not damaged, but you can see that there are creases on the scan. So machine learning algorithms also don't understand this, and they will kind of try to separate this in two columns. On the other hand, things are very close here, because everything was done by hand back then they will see this as one line that goes through. So if you say, no, this is not something to divide, it's just a crease, then it will also move away this. So with a machine, this is very difficult, but if we are looking at this the way that we humans do, why can we do that? Well, we actually read and see that this text continues. We also group text in a way. We can recognize, even if you cannot read Arabic or Chinese, or you will be able to see it's text. It's the way that we humans structure text. So we do pattern recognition on text that is human generated. So we created a machine learning algorithm, but not by example, but by learning from the page itself, by looking from a pixel around the area, like what is looking similar, what is looking grouped, what is looking different. And so this allows us to group that into paragraphs and also detect damage. So yellow means a high probability that it's damage and not text. I said that we're also using text with it so this is purely on looking around, but now of course we want to use LLMs to kind of also get all the information that is there and to automatically realize that. So, well, how do these LLMs work? How can computers now learn text? Because it's also an image. So sometimes it's thought, yeah, maybe they learn them from the characters. But that's a completely different mathematical structure. What you do there is actually learning text by context, by looking around words. And ChatGPT, for example, is being trained by giving it lots of text. And there you don't have labels, so it kind of creates its own examples by just looking at which words are appearing often next to each other. And of course, work and dove, they will not appear that much to each other, but work and yesterday will happen or will occur a lot. What is done then is that these words are getting coordinates. So the mathematical structure that you use for words are not matrices of numbers, but coordinates. And words can be cut in pieces, and you actually use 50,000 pieces. And 50,000 pieces are enough to create all words in English and other languages. And we give them coordinates. Coordinates, we often know them like on a map, then it's two-dimensional. But ChatGPT works with a 12,000 dimensional space. So you get 12,000 coordinates, and those coordinates are between 0 and 1. So this runs here to 12,000, and you again do this randomly, and then you check text, and you move words that are close to each other, close in coordinates. So this is taking a lot of time, a lot of computing power, and then since 10 years, we have also this technique, but it's of course possible because of computational power to not only look next, words that are next, but then look at all sentences, and this is attention. And then this can detect that even though we see 2 times interest, that the first interest is actually a synonym for enthusiasm, and the second interest is more into the context of financial. So in this big space, if you can look further than words that are just next to you, you can, especially if you have 12,000 coordinates, there's room enough to move words and closer or farther apart. And then words that mean something similar actually get similar coordinates. And then if you would plot them two-dimensional, you'll see them in groups appearing, like transportation means where you would go to would be close. So this is what we call the embedding space, and it will give you, for every question that you ask to ChatGPT, it will compute where in the space do I end up, and then it will answer you with something that is lying around that. Again, it doesn't understand, but it's very impressive if you can give it all of the internet and all of the scanned images that you have. But if you give it like complicated documents, like technical documents for industry, again, it goes wrong. And that's again where we, with digital mathematics, come in, because we then look like these tables and these graphs. How do we read this as humans? We can again tell a machine how to do that. We read like the headers, and so we can, using images, make LLMs smarter and also learn from documents where current systems cannot deal with. And of course, if you have text, then you can also combine it with images, and then we see these very nice generation things like a dog vlogging on Maui. It's very impressive. You'll see a bird flying by. Yeah, the shadow is there. It's amazing. This is created by OpenAI. They also have this one on their site. Now you see things going wrong. This one is also funny. This is archaeologists finding objects, and you'll see a plastic chair. It's a sturdy one, but now you'll see it suddenly folds. Yes, plastic chairs are often foldable too. Running backwards. Yeah. Why I showed this? Well, again, these networks, they're very, very good, very hardly, deeply trained. They have a lot of examples seen. They have the text that describes what is there, and so on. And so my story is, yeah, images, with the computer, you can understand them. But now the question comes with the mistakes you see. We actually see those mistakes because we live in space. Will AI ever be smarter than us if it doesn't live in space but just uses images? Can we, flat, understand our whole world? I don't think so, right? So I think in all what we see, like, oh, AI is going to be smarter than humans, you have to use it as a very good tool, very efficient tool, but it's at this point nowhere to be as smart as we humans in the 3D world. And if I ask it to create an image of a math professor, and it also runs into bias, we get a blackboard, right? We like blackboards. But professor, yeah, that has to be with a coat and, of course, a middle-aged man. And if I ask it a female professor, so, well, take pictures, tag, let those networks train on real mathematicians, women mathematicians like Miriam Mirzakhani and all, and let those networks become better. Thank you very much.
Thank you very much, Anna, for an amazing talk. Es tiempo para alguna pregunta breve antes de terminar la conferencia.
We have time for some brief questions before ending the session. If someone in the room would like to ask a question, please go ahead.
Maybe I can break the ice. So you were telling or showing us some images after training the network. So what happens, or how could we discover that an image is fake if we don't know with which information we can train the network to distinguish things?
Yes, that's a very good question, because it's a very difficult problem. What we are, I have a student currently looking at this. What you can do is, and it will again be about this global and this very local and this detailed structure, is trying to learn again what is the combination of pixels and structures that, for example, these diffusion models make, and yeah, try to kind of see if it's more deviating from real-world images. Now, the problem with that is that every time you would actually be able to see that, you can then train a network to kind of undo that and to make it look more real. So it's a bit cat and mouse. So this deepfake detection with neural networks themselves, it's always going to be a changing game. And they become very, very realistic, of course. So that's kind of problematic for news agencies. So we might have to look at other kinds of ways to trust images, like stamps, authentication, and some other way. Yeah.
¿Alguien se anima ahora?
Would someone like to ask a question?
I was wondering, because you were talking first about compression of images and then about classifying images, and I was wondering if it will be easier to classify an image like the original version or the compressed version without details.
Well, it's when it's this classification, when you're looking at actually distributions of objects, it won't look into the details that much. So there, the compressed version, of course, if it's not too hard compressed, but the compression will actually not matter. But if you're looking for learning painting style, then compression would actually fade out the small details that you see. So classification, no, but learning to generate, then it will make a difference, yes.
Bueno, pues si no hay ninguna... Ah, sí, otra por ahí.
¿Lo tengo que decir en inglés o...?
No, no hace falta. And so I think you need to use the headphones, so...
Yeah.
Or I can translate it.
Gracias por tu conferencia, ha sido muy interesante. Me ha parecido genial el experimento de sofonisma de Anguissola y Alonso Martínez, porque durante años los cuadros de sofonisma decían que era de Alonso Cano. ¿Cuándo se descubrió al revés?
It was in Spanish.
I can try, but yes. So she was asking about the experiment with Alonso and so.
Yeah.
I guess that works.
Yeah, that I got.
So for a long time it was thought that los de Alonso.
Que las pinturas de sofonisma eran pintadas por Alonso Cano durante
Okay. So for a long time it was thought that paintings from were painted by Alonso Cano, and it took a while until they discovered it was the opposite.
Yeah, exactly. And that is what we're going to... Yeah, so that's what we will investigate with our experiments. But we would need, in order to learn the style of Sofonisba and Alonso, we would need paintings that are 100% sure painted by each of them separately. You also have the problem with workshops. Probably with Alonso, his paintings will maybe be more difficult to learn his style because he was mostly using people to kind of do some details, or while Sofonisba is most likely the one who would have painted it whole. So it is a bit of a problem with bias of learning with Alonso, that we will not be able to know for sure which pieces of the painting are. It's now in the Courtauld. We're working with the Courtauld. There's a PhD student, and she is planning to come to the Prado to get more pictures. Yes, but now we only have the one scanned in the Courtauld, where there's of course not enough data to investigate further.
A ver si...
Yeah.
Que va a ser un poco raro. Bueno, muchísimas gracias.
Thanks very much. Can you hear? I loved your speech. I have nothing to do with mathematics, but it was great. It is Channel 4.
Spanish.
Está en español.
It's Canal 4. Okay. Yes.
Okay, can you hear me now? Can you hear me now? Yes? Okay, vale, okay. No, I'm talking in English. No, I'm talking in English. No, it's Channel 4. It's Channel 4. I don't...
Side, but he enjoyed a lot the talk.
Me estaba preguntando que de la misma manera en que cuando hacemos una...
I was wondering, just as well, when we take a photo, it is translated into numbers. Can we predict through probability or somehow the movement that led a person to pose in that way, for example? And can it be predicted? Can we predict in the same way the movement that followed the fixed photograph? I'm talking about a theater setup, for example. Is that possible? Is someone working on that?
Well, it would be then connecting, of course, with the physical movement. So if it's just an image, then what data would you have to give? But in the context of compression, it was already needed to better compress, not to have these artifacts that you saw, to take a bit of this movement. So there is research in compression, video compression, that also takes a bit of the 3D world with us. So yes, I would assume that if you combine these techniques with an AI engine, that it would be able to kind of generate what was before, because that's what you would like, what was before or what it would come after, or yes, but you would need some 3D awareness, because currently, they're like the guy that was running backwards. You could have still weird things, but it's a very interesting idea. Yeah. Thank you.
Bueno, ya ha llegado el momento de terminar con...
And now there comes a time to end this session of the mathematics cycle for today. Thanks very much to all of you for having come. Thanks especially to Anne for having illustrated us with this very, very good speech. Thanks very much.